Hi folks, this is my attempt at a video lecture here, coming to you live from the House of the Flu. So, I think the easiest way to do this is to go through this handout with you. I encourage you to print this out first, or even after watching the video, but then to watch the video again and go through it on your own and take the same kind of notes that I'm taking so that you can, put your thoughts in order while I'm putting mine in order. So, we're going to pick up where we left off in Chapter 9, when we had just finished gushing about the possible analogies between our normal linear kinematic variables, position, displacement, velocity, acceleration, and the perfect alignment to the rotational kinematic variables, the angular position, angular displacement, angular velocity, and angular acceleration. And this was great. And we look back to our first few chapters, and the next thing we talked about after acceleration was Newton's second law, F equals ma. And so I think it's pretty natural to ask, is there a rotational analogy for Newton's second law? Something like mass times angular acceleration or something like that. And I don't know that it's a surprise. We'll see that there is such a thing. But on our way there, let's start with energy. So consider a rigid extended body that rotates with angular velocity omega. So this is a non-uniform object. This is the drawing I came up with. It doesn't need to be any particular form factor. It doesn't need to be any particular shape. It's non-uniform, just to keep things interesting. And we're going to rotate it around some axis here through the object. Let's rotate it this way. Okay. Divide the body into individual mass chunks, m1, m2, m3, all the way up to m sub n. All right, fine. So I'm going to redraw the object. I'm going to try to redraw the object. And redraw that axis. And then I'm going to consider individual little chunks, little cubes of mass. And then, they're really all through the thing. So there's, n of them, n is some super large number. And ask about the distance each of those masses is from the axis of rotation. So if this is mass 1, then we've got his distance from the axis of rotation as r sub 1. If that one's m2, then we've got her distance from the axis, r sub 2. If this is mass 3, we've got r sub 3, and so on. And we do that for all the n masses we've got. If we pick a random index I, and we say, hey, mass number I, come on up, you have some linear speed according to that formula we got last week. The angular speed times the distance away from the axis of rotation. So if we know v, we can calculate the kinetic energy. Because remember, speed is all we need for kinetic energy. It's a scalar. So we could plug in, for v here, we could plug in r omega for the ith little mass chunk. Okay, so if we wanted the total kinetic energy of the entire body, then we got to add up all the kinetic energies of all the little pieces from 1 to n. So we take this expression, we add it, we sum it from 1 to n, and since omega is the same for every chunk, every little mass piece, it has the same omega. That was we were so happy about omega, is that it's the same for every point in a rotating body. We can factor it outside the summation. And that leaves us with, I'm just going to write it up here, 1/2 omega squared times the summation of mass number I times its distance from the axis squared, summed from 1 to n. This summation, this expression here, its job is to quantify how the mass is distributed relative to this axis of rotation. So it's a rotational mass distribution, or I'll emphasize it's a rotational mass analogy. When we're trying to rotate an object, we care about which axis we're trying to rotate it. The inertia of that object's mass speaks differently. And if you don't believe me, find an extended object like a baseball bat or a tennis racket and spin it end over end, and then spin it longitudinally. So in other words, take it and spin it this way, and then try to take it and spin it this way, just longitudinally about its axis. One of those will turn out to be much, much easier to do, and that's this idea, this rotational mass. So it's not really rotational mass. We'll give it a fancier name. Let's call it moment of inertia. Now, moment is an old word from the engineering disciplines, and we've already actually seen one moment. The first moment is the center of mass, and it's the summation of mass times just r to the first power. So what we're doing here is the second moment about some axis. Let's use the symbol I, and somewhere along the way I got into the habit of drawing two vertical lines for the capital I. I don't know why, and now I can't stop. So just it's not a Roman numeral 2, it's a capital I. And we're going to define that to be the summation over the object of mass times square distance from the axis of rotation. Now, in a rigid extended object like a baseball bat, how many masses should you include? I mean, really, it's a continuous object. So, it sounds like an integral, right? It sounds like a Riemann sum. So we can write the integral. We did the same sort of trick with center of mass back when we did it. It's the integral over the volume of the object, r squared dm. Now, and contrast that with the position of the center of mass, which was just the first power of the distance away from the origin. And instead of the origin, in this case, we're talking about the distance away from the axis about which we are rotating. Okay, so let's try one or two. I'll move on to the next page. Okay, so find the moment of inertia of a hollow cylinder of uniform mass density with length L, inner radius R1, and outer radius R2. Okay, fine. So, uniform mass density, again, that makes me think of the problems we did calculating the center of mass of something with an integral, with a uniform density, and we just assumed some variable rho that was that density, and we ran with it, and then eventually we absorbed it into the total mass of the thing anyway. But I think let's do something similar here. We'll start with the new definition of the center of mass, or moment of inertia, rather. The integral over the volume of r squared dm. And as soon as we write this, again, I'm thinking about center of mass and what we had to do to write dm in terms of r so that we could actually integrate. It also makes me think of path integrals, like the Throckmorton problem. We had to find one scalar variable to express the integrand in so that we could actually integrate. Okay, so that I'm looking to unpack dm the same way we did for center of mass. Now, the problem gives us a hint. It says the volume element we're talking about is a cylindrical shell. So like the label on a soup can, or the label on a soda bottle, with some radius r and some thickness dr. So imagine we cut this label off the can and we rolled it out in front of us. It would be a thin sheet. It would be a sheet L tall, dr thick, and have a length equal to the distance around the soup can, or the circumference. So here's my thought. Circumference height thickness. Take a minute, think about that, convince yourself that that's true. And I'm going to use a little r here instead of a large constant capital R, because we're going to let these soup cans get larger and larger from the inner one at R1 all the way through the material of the object, from R1 all the way through to R2. So I want this R to be a variable. I want it to be this R, in other words. Okay, and with that assignment, we can proceed through our integral. Integral over the volume, r squared 2 pi, whoops. See, I talked about it and then I forgot it. This 2 pi r L dr isn't actually dm. This is dv. It's volume, circumference, height, and thickness. If we want to talk about mass, we need to include that density that I just talked about. Okay, so we'll bring that with us. 2 pi r L dr rho. Now we can factor some things out here. 2 pi L rho, those are all constant. And we're integrating r cubed, because we've got r squared and r, dr. And since r is the only variable here, r is going to run from the inner radius, r1, to the outer radius, r2. Okay, so we integrate and we end up with pi L rho over 2 r2 to the fourth minus r1 to the fourth. And the 2 that was here is canceled partially by the 4 that we got in the denominator from the antiderivative. I just did that step all at once. So take a minute, verify that that's the real antiderivative. Now, this problem, this is a worked example in the textbook. It's worked example 9.10. Worked example 9.10. And if you go to worked example 9.10 and look up the answer, it's not this. And the reason for that is that we'd like to express the moment of inertia of the large macroscopic size object according to its total mass. And there's nothing here that talks about total mass. We can talk about total mass if we talk about the total volume. Remember, mass should be density times volume. So what's the volume of a hollow cylinder? Well, it's the volume that is the outer cylinder minus the part that's missing, the hole in the middle. So we've got pi r squared L, but this is the outer radius, so it's R2, minus the missing cylinder's volume, pi R1 squared L. That's the volume of this hollow cylinder. So we can factor out the pi and the L and end up with R2 squared minus R1 squared. And that's not quite what we've got here. I don't see a volume, except that this is the difference of squares, and we can factor that. We could factor that so that the moment of inertia, pi L rho over 2 R2 squared minus R1 squared times R2 squared plus R1 squared. And here we've got pi L R2 squared minus R1 squared. And we also have the rho that we need to multiply by the volume to get the mass. So most of this is just the mass of the cylinder. And we're done. That wasn't so bad. Most of the time, we won't need to find a moment of inertia this way. The next problem here says to verify the moments of inertia reported for a thin rod of length L and mass m upon an axis through its center and an axis through its end. Now, verify means I must have given them to you first so that you can check them. Most of them, for a handful of regular objects, are in table 9.2 on page 286 of the textbook. And on an exam, for example, I'm just going to provide that table for you. So you can look forward to that. I'm going to leave this exercise 2 here for you. It's worth doing. Follow the same method that we just used and see if you can achieve the answers that table 9.2 reports. Okay, sorry about that break there. I had to blow my nose. So let's turn the page to page 3. Now that we have defined moment of inertia and know how to calculate it, we can finish the formula for the kinetic energy associated with rotation. 1/2 I omega squared, which looks a lot like the old formula for kinetic energy. I'll call this linear kinetic energy, 1/2 mv squared. And we just see the rotational analogs again. The rotational mass analogy in moment of inertia, and the rotational version of velocity, or speed. So I'll put rotation here. Now that we've defined kinetic energy for rotation, we could use it just like we can any other kinetic energy. We can use it, say, in the work energy theorem. So let's take a look at what that might look like. A light non-stretching cable is wrapped around a solid cylinder, okay, of mass 50 kilograms in diameter, 0.12 meters, that rotates in frictionless bearings about a horizontal axis. The cable is unwound by pulling with a constant horizontal force of 9 newtons for a distance of 2 meters. The cylinder turns and the cable doesn't slip. So this is that smoothly rolling thing that we talked about. Find the angular speed of the cylinder. Okay, fine. Now, I see a force and a distance, and that makes me think work. And I know that I can find final angular speed using kinetic energy. So I just think about the work energy theorem. I guess if we're being really careful, we'd have to talk about the change in rotational and the change in linear kinetic energy. But these bearings, it's not rolling along the floor, it's just turning on frictionless bearings. There's no horizontal motion at all. There's no linear motion of the center of mass of the cylinder. So that's not going to change. Okay then, So the only work done is the work done by this applied force, and the only kinetic energy change is that of rotation. So, fine. The force applied dot the displacement, that's the work done, and that's 1/2 I omega squared minus I think we're supposed to assume that the cylinder was initially at rest. Otherwise, I don't know if we can answer this. So I think let's assume the cylinder was not originally rotating. The dot product here, the force and the displacement of that rope, that cable, are in the same direction. So I think we just have the magnitude of the force, the magnitude of the displacement, and the cosine of the angle between them, which is 0. 1/2. Now, we need the moment of inertia of this kind of mass distribution. So we go look in table 9.2, and we see that the moment of inertia of a solid cylinder about a longitudinal axis and again, this is just from table 9.2. We didn't have to calculate that or anything, although we could have. 1/2 I omega squared. And this is omega final. Okay, so let's see. The mass we know is 50 kilograms. The radius we know is 0.06. Be careful, not 0.12. This is diameter. So we can calculate omega final with the square root. 18 joules. Division by the half multiplies by 2. Mass of 50 kilograms. The square of the radius, 0.06. And we end up with, check my math on that, 14 radians per second. Okay, so again, I'd like the moral of the story to be how seamless the transition from linear kinematics and dynamics to angular kinematics and dynamics actually is. All of the concepts connect the same way. It's just a rotational version of all of our previous work. Okay, we started this worksheet asking about Newton's second law and whether there's a rotational analogy for that as well. Now, that's fine if there is such a thing as rotational force. There's two things we want to happen. It should, I mean, if any sort of symmetries exist in the universe, it should be rotational mass times rotational acceleration. So whatever the thing is that is rotational force, we want it to be equal to rotational mass times rotational acceleration. Okay, so that's thing number one. Thing number two, work usually equals force dot displacement, like we just used. So work should still equal rotational force dot rotational displacement. So work should equal whatever this thing is, rotational force dot rotational displacement. And now we hear the record scratch and all the motion in the room stops. Oh, I don't... This is a dot product. It's a vector thing. In order for this analogy to work, force and displacement were vectors that we could take the dot product with. That means whatever this is, we didn't treat vector nature of angular displacement last week. And it also means that whatever this is, this rotational force, also has to be a vector, because work needs to end up as a scalar. Okay, so this question mark here is a vector. Rotational mass, I think, needs to be a scalar. We only multiply scalar things to find it. But that means that in order for this equation to have vector nature on both sides, the angular acceleration needs to be a vector as well. Okay. So we've got to go back to the drawing board and fold in the vector ingredient that our, batter is still missing in order to bake this rotational pie. So, I'd like us to think again about a simple circle and some small rigid object that rotates around the circle, like, for example, the second hand of a clock face. And I'm going to draw it so that it's actually going counterclockwise, just to be confusing. So imagine that there was some rigid object that was rotating around a circular plane like this with some angular velocity omega. Had to get a sip of water. Our work on Thursday let us know that the tangential velocity of a point at the end of that object, or at least the tangential speed, was omega times r. Excuse me. Now, all right, so really, we should have wanted all along for tangential velocity to be a vector quantity. If we wait for some amount of time, this object now is over here, and if we ask for the tangential velocity there, points in a completely different direction. So we knew all along, I think, that this needed to have some direction built into it. Now, if velocity is a vector, and this is angular velocity, I think it's pretty natural to want omega to be a vector as well. There are two problems with that. The first problem is that, well, in what direction, right? Velocity is pretty clear. It's tangent to the path in the direction we're going. So what direction is omega in? And then the other, maybe even thornier problem, is the fact that the tangential velocity changes direction constantly. As we go around this circle, the tangential velocity changes direction. What we liked about omega is that it was constant, and it describes the motion of this object as it goes around the clock face, and it doesn't change. And, we think about uniform motion in a circular plane. Okay, it's a constant rotation. I don't want the direction of omega to change, because it's all the same rotation. Whether we're here or here, it's all rotating counterclockwise with angular velocity, or angular speed, omega at least. So I totally agree that we want this to be an angular velocity, not just an angular speed, but that means we've got to figure out, A, what direction it points in, and B, how to reconcile the changing directions on either side. Okay. Now, What if we talked about a point halfway along this object? And you did this calculation on the previous worksheet. It's not the entire distance away from the axis. It's just the distance to where we are. So I'm going to use not capital R, not the whole radius of the thing, but little r, just to underscore the fact that, sort of like in the moment of inertia calculation, that radius can change. It could be anything from zero all the way to capital R. In other words, I want this variable to do the job of answering the question, which radial position are we talking about? Now, okay, that's fine. It's a radial position, that's great. But do we really need to say radial? What if we just said which position we're talking about? What if we just let this be a vector? Not which radial position, but which actual position. Now we're getting into strange territory. We haven't had something like this before. We're trying to multiply, hypothetically, two vector quantities and end up with a third vector quantity. And it turns out we've already developed machinery that can handle that for us. The only way we can multiply two vectors and end up with a third vector is with the cross product. It's the only way we can do it. Okay, so now we really need to know what direction omega is in. And the answer comes from how we know the direction of the cross product is calculated. It's according to the right-hand rule, right? We ask for a vector whose magnitude is the magnitude of omega, the magnitude of r. We multiply by the sine of the angle between, oops, I don't want to use alpha, the sine of the angle between them. And that's the magnitude of the result in a direction perpendicular to both of them, according to the right-hand rule. Okay, so the tangential velocity, we're saying, hypothetically, hopefully, needs to be in a direction perpendicular to both omega and r. Now, that's fine, I guess. It is always perpendicular to the radial direction, right? We ask about radial position r, and we're drawing out along the object to here. The tangential velocity is always perpendicular to a radius. So we've got that going for us. But we can't pick another vector in the plane of the page. V, tangential, is in the plane of the page. If we picked another vector, something, on the x or the y axis for omega, then we would preclude the tangential velocity from being in the same plane as those two vectors. It needs to be perpendicular to both of them. The only way that works is if omega is in the direction perpendicular to the plane of rotation. So we've got rotation in what let's call the xy plane. Omega, in order for this to line up, needs to be out of the page, at us, at our face. And remember, we do this with the right-hand rule, right? If omega is out of the page, then omega points up. Let's see. How do I do this on the camera? We point our fingers in the direction of omega. We point our palm in the direction of R. So my palm is pointing this way now. And wait, there we go. Fingers up in the direction of omega, palm out in the direction of R, and my thumb now points in the direction of V. It can take some getting used to, and this presentation is not the best. We'll circle back to this, no pun intended, as we go, and I can give a more convincing demonstration in person. But the takeaway here is that omega needs to be a vector in the z direction. And if the rotational chapters are confusing, I think it's because of this three-dimensionality. It's our first time that we're dealing with explicitly three-dimensional scenarios. We've got a rotation in a plane, and we have to consider a vector perpendicular to that plane. We measure angles as positive when they are counterclockwise with respect to the positive x-axis. So let's do that with omegas as well. Positive rotation is counterclockwise rotation. Another way to see that is to again use a right-hand rule. If you take your fingers and curl them in the direction of the rotation, your thumb points out of the page in exactly the direction we said omega needs to point in the positive z direction. Okay. So, wrapping this up, we can talk about a vector angular position, which again, if omega is going to be in the z direction, now let's work backwards. Omega is delta omega over delta t. And the only way that works in the z direction is if delta omega is also in the z direction. And the only way that works is if omega is in the z direction. And in the textbook, you'll find out that a lot of the time they aren't explicit about this vector nature. They just call it omega z, because almost all of our rotations are, constant in a plane. So, okay, let's define the xy plane as the plane of rotation, and then omega is always in the z direction. So they can just say, all right, let's talk about omega z. Okay. So let's keep going and try to nutshell some of these results and then put some things together. we had tangential velocity is omega cross r. And if we modify our formula for tangential acceleration as well, we can use alpha cross r. Okay. Now, we want rotational force to be equal to moment of inertia times angular acceleration, which I guess is a vector now. Okay. And we want it to be a rotational analogy of Newton's second law. So I'm going to suggest we start with Newton's second law. And for this derivation, let's consider just an object moving in a circle. There's no extended object. I just want to be kind of careful and go a little bit slowly through the derivation here. So we just have a mass. Maybe it's at the end of a very, very, very light string, and it's just swinging around in a circle. If we're going to change its angular velocity, change the rate at which it's going around in a circle, that means we must have exerted some sort of rotational force to speed it up or slow it down. Okay, and that should be somehow relatable to net force is mass times acceleration. Okay. Now, for reasons, I'm going to suggest, and as long as we do this to both sides, we can always do this. I'm going to suggest taking the cross product of vector r from the left on both sides of Newton's second law. Now, mass is a scalar, so we can multiply that before or after, it doesn't matter. So let's pull it up front. And if this is all we're talking about, just rotation and not translation or anything like that, then the only acceleration is the tangential acceleration. So m r cross, and instead of the tangential acceleration here, we could replace it with what we know that it's equal to. Alpha cross r. Now, if you're curious, this vector triple product, there's an identity that relates that to something a little bit more useful. And there's various proofs that you can find online. But for the sake of argument and expediency, I'm going to ask you just to trust me. It can be shown, which is how the textbooks say it all the time, that this is equal to the first thing dot the last thing, which yields a scalar result multiplying the middle thing, minus the first thing dot the second thing, a scalar result multiplying the third thing. Now, at first glance, that doesn't look all that better, but r and tangential acceleration are perpendicular, which means the dot product of those two things is 0. And r dot r, well, any vector is parallel to itself. So that's the magnitude of the one times the magnitude of the other times the cosine of 0. So that's just r squared. So this reduces to mr squared alpha. Now, if we think about just one mass rotating in a circle, what is its moment of inertia? Well, it's the sum of mr squared. But there's only one, so it's the mass of the thing times its distance from the axis of rotation. Mr squared. There it is. So this quantity over here, r cross net force, is equal to moment of inertia times angular acceleration. This is exactly what we wanted. So this thing must be rotational force. So let's give it a name. We'll use the Greek letter tau, which looks like a capital J in a mirror. We'll call it torque. If we want the net torque, then we're doing r cross net force, which would be the net torque. And if we follow along from here, that's supposed to be equal to I alpha. And there's our rotational analog of Newton's second law. Rotational force equals rotational mass times rotational acceleration. What are the units for torque? Well, that's meters times newtons, which, oh gosh, that's newtons times meters. That's usually joules. But because joules is a unit reserved for scalar quantities, like work and energy, let's just agree to leave the units for torque, as meter newtons. We do need the dot there, the times, so it doesn't look like mn, millinewtons, right? We don't want it to be a metric prefix. We want it to be meters times newtons, meter newtons. If you've worked around cars, they sometimes, folks talk about foot-pounds of torque, like a torque wrench or something like that. And it's the, English version. Foot-pound, length force, meter newton. Okay, so speaking of work, does it do what we wanted? Work should be equal to rotational force dot rotational displacement. Now, if we sped this thing up, it's because we exerted a force tangent to the thing. And torque, it turns out, is in the same direction as alpha, which is in the same direction as delta omega, which is in the same direction. So it's all in the z-axis, in other words. Torque is in the z-axis. So is delta theta. So this dot product doesn't really do a whole lot. These are already parallel by definition. Or maybe anti-parallel. If we're exerting a torque to slow the thing down, for example, it's still rotating counterclockwise, but we're trying to push it back the other way. Okay, so it could be positive or negative. So I'm going to leave the dot product here, but the cosine phi part we will never need because these are always only parallel or anti-parallel. All right, so does it actually yield joules? Well, yeah. Torque has the units of meter newtons, dot radians, and as soon as we dot, we end up with a scalar result. And we can go back from meter newtons as soon as we dot product, we can talk about a scalar unit, and now we can talk about joules again, just like we wanted. This is great. We have rotational analogs for pretty much everything, for force, for work, for mass, for acceleration, the whole bit. And I'm going to attach a formula sheet that goes through and lists different formulas for linear motion, rotational motion, and the combination, rolling. The punchline here for rolling is that as we're rolling, we are rotating with angular velocity omega, but we're also moving to the right the entire object with some velocity. So rolling, we could think of as the sum of rotation and translation. And in fact, the kinetic energy associated with rolling is just the kinetic energy associated with rotating and the kinetic energy associated with linear motion. This doesn't have a whole lot to do with what we just said. We just had finished the job of developing Newton's second law for rotation, and now we say, okay, well, we've got this kinetic energy thing. What else can we do with it? As soon as we talk about this, we can put rolling, remember the smoothly rolling conditions. That relate the motion of the center of mass of an object to the rate at which it's rotating. Now, let's consider one more example, and then I'll leave you to examine the rest of the chapter on your own. A primitive yo-yo has a massless string wrapped around a solid cylinder. So, we just took one of the cylindrical kilogram masses from the lab and wrapped a string around it. A solid cylinder of mass m and radius r. When you hold the end of the string and release the cylinder, the string unwinds but does not stretch or slip. So in other words, the cylinder unrolls at the end of the string. We are supposed to find the vertical linear speed of the yo-yo after it has descended a distance h. Take a minute, think about the physics involved, think about the variables that are initialized by the problem and what they telegraph to you. I'm going to use the minute to blow my nose. Be right back. Okay. So, here's what I'm thinking. I am thinking that does not stretch or slip is an indication of smoothly rolling. Now, I've got a relationship for rolling, so I can talk about the change in the kinetic energy of this thing. Height h. It's descending a distance h, and that makes me think about potential energy. So this makes me think about energy conservation. There's not actually much more to this than just dropping an object from a height h and trying to figure out its speed after h. We just need to include the rotational component to the kinetic energy. All right, so let's try the work energy theorem. Now, non-conservative forces. The only non-conservative force that's acting is friction. But the thing is, for smooth rolling, that point of contact on the surface or against the string is instantaneously at rest, which means the friction that acts doesn't cause any displacement, which means the work done by friction is zero. At least in theory. Okay. So then we start unpacking the terms on the right-hand side. Delta K. So that would be delta K rolling, because we are does not stretch or slip without slipping, smoothly rolling. Okay, so we're rolling. So this is delta K rotation plus delta K linear. And this linear one is the one we want, I guess. Plus delta U. Okay. So, from rest, fine. 1/2 rotation. You remember what it is? Rotational mass times rotational velocity squared plus minus 0, but we started from rest, so that's okay. 1/2 regular mass, regular velocity squared minus 0. Delta U, so this is plus mg negative h. We're going down, so our potential energy should decrease. Okay, but it looks like we have too many variables. It looks like we have omega v. M and r and h were initialized for us. So this m, we got those. H we were given. So those are okay to use in our answer, but omega and v, I don't know anything about omega. V is what I want. And this is where we can leverage the smoothly rolling condition. The omega of the center of mass of this yo-yo is related to the linear speed of the yo-yo body. In other words, because it's smoothly rolling. So 1/2. Now again, it's a solid cylinder, so we go look up the moment of inertia in table 9.2, and it's still 1/2 m r squared. Omega in terms of the linear speed of the yo-yo body is v squared over r squared plus 1/2 m v squared. I just switched to capital M because that's what was initialized in the problem. Plus mg negative h. And we want to solve for v. Okay. So let's move mgh to the other side. Let's cancel m from every term. The r squareds here cancel. And 1/2 times 1/2 gets us 1/4. That's 1/4 v squared plus 1/2 v squared. So that's v squared 1/2 plus 1/4 is 3/4. So that's gh equals 3/4 v squared. And then we solve for v. And it's 4 over 3 gh square root. If this had just been a falling object, no rolling, the answer you might remember from some of our conservation of energy problems, it would be 2gh. So this 4/3 is 1.33, so it's less, because some of the potential energy that we converted into kinetic energy has to be shared as rotational kinetic energy. Not all of it can go to the linear kinetic energy like it used to. Now we're rotating in addition to translating. So some of the energy that we get by converting our potential energy has to go to the rotation. So our linear speed is a little bit less. Okay. Again, I urge you to print out this worksheet. I've attached a blank copy. I've also attached the filled out copy. And I've attached this video. And I urge you to watch the video with your own blank copy and take your own notes. It really will help with the attachment to the concepts, I think. Once you're done, also check out that formula sheet that I'm going to post that goes through linear, rotation, and rolling. And then on your own, read over sections 10.5 to 10.7. And 10.6 are about angular momentum, which goes very much like we expect it to. We're going to use the symbol L, but it's rotational mass times rotational velocity, just like regular momentum is mass times velocity. No surprises here. 10.7 is a little complicated, and we will go over that the next time we have class in person. Okay. Thanks, folks. Let me know if you have any questions. Take care.